For our second example of a randomized algorithm, we're going to look at the min-cut problem. This is secretly the same as the max flow problem that we saw earlier, but I'm not going to talk about that. There will be something about that in the supplemental material. So the input here is a graph, and the output is the minimum size cut in G, where a cut in a graph is a set of edges where when you remove those edges, the graph becomes disconnected. So for example, if this is our graph, if we remove this edge, then the graph becomes disconnected. Okay. So in this case, the minimum cut is this edge and it has size 1. And if there's more than one minimum cut, we don't care which one you output. Okay. And in general, you could do this with a weighted graph, and then the weight of a cut is the sum of the weights on the edges, and you want to minimize that. This has all sorts of applications, essentially the same as we discussed in max flow, but you could imagine this as a network of pipes or a network of roads, a network of power lines, that sort of thing. Okay, and so there are some obvious things you can say. For example, the minimum cut is always at most the smallest degree of any vertex. Because if I take a single vertex and I just cut all of the edges that touch that vertex, then I've separated the graph. Okay. But in general, the minimum cut can in fact be much smaller than the minimum degree of a vertex. So we can build a similar example here. All right, so here every vertex has degree at least 3, but again, the minimum cut is still 1. Right? And you can generalize this if you replace each of these things with a complete graph on n nodes here. Every node will have degree at least n minus 1, but the minimum cut will still be 1. Okay. All right, so now what I want to show you is a very simple randomized algorithm for this due to David Carter. And we'll go back to our smaller graph. The idea here is pretty ingenious, but quite simple. And it uses one basic operation, which is called a merge. So what you're going to do is you're going to pick 2 vertices at random, because it's a randomized algorithm, and you're going to merge them. So say we pick these 2 vertices. What the merge does is it merges those vertices into a single vertex, but it keeps track of all of the edges. So after you do this merge, your graph then looks like this. So now these 2 vertices have been merged into a single vertex. There was an edge between them, but we're not actually going to care about self-loops like that. So we're just not going to keep track of that sort of thing. But we are going to keep track of the fact that from this vertex to this pair, there were 2 edges. Okay, so that's the result of this merge. And the algorithm is you just keep picking pairs of vertices at random and merging them until you only have 2 vertices left. So let's see, for example, what happens here. Maybe I pick these 2 vertices to merge. So you see, there will be one vertex here with just a single connection. Maybe then I pick these 2 to merge. So then I get a sort of similar looking thing to what I had before. So this is my new merged vertex. It has 2 edges. And then maybe I pick these 2 to merge. I'm left with a single edge, and then I cut that. So when you get down to 2 vertices, you'll have some number of edges between them, and you cut all of those edges. And then a relatively simple analysis shows if you sort of backtrack and you keep track of, for every edge that I see here, where did it come from in the original graph? If you cut all of those edges, that actually is a cut in the graph. Okay, but it's a randomized algorithm. So, in this case, I just so happened to pick a sequence of merges where we ended up with just a single edge to cut. And obviously 1 has to be the minimum unless your graph was disconnected to begin with. But it could have gone differently, right? So let me start from here, right? So I did this merge and I ended up with this. And then say I merge these 2. I have this. Maybe I merge these two. So I end up with this. And then maybe, unintelligently, but part of the point of the algorithm is that it's so simple that it doesn't have to be intelligent. I merge these two. And then I'm left with this. And now I'm cutting these two edges. And I think, if I kept track of this in my head correctly, that those two edges correspond to cutting these two edges here. Right? So in this case, I made some random choices where I didn't actually get the minimum. And what we would like is a guarantee of, well, what's the probability that you actually do get the minimum? And it turns out that a relatively simple analysis, which I am not going to do here, says that the probability that you actually find the minimum cut by this procedure is at least 1 over n squared, where n is the number of vertices. Okay, now for a large graph, that may not seem very good, but if you run this very simple algorithm n squared times, then the probability that at least one of those finds the minimum cut is around 63%. Okay, and 63% now seems a lot better than 1 over n squared, certainly when n is large. Okay, and now there's a standard trick with randomized algorithms, which is if you have a randomized algorithm where it does what you want with a probability that's strictly bounded away from a half. So it's not like a half plus 1 over e to the n. This is, a constant number that's strictly greater than a half. Well, then just by running this algorithm 10 or 20 times, I can get it to the point where the probability that it outputs an incorrect answer, in this case a non-minimum cut, would be less than 1 in a million. Right? And if you run your algorithm then say 80 times or 100 times, you start to get to the point where the probability that your algorithm made an error is actually less than the probability that a cosmic ray came down and hit your computer and messed up your memory, which would have messed up your algorithm anyways. The other thing to note is that I said, okay, in order to get to this point of 63%, so this is the starting point where we can use that standard trick and then we can make the error as small as we want. But in order to get to this point, we had to run this algorithm n squared times. That may seem bad, but if you recall our algorithm for max flow, actually the running time between running this n squared times versus the standard algorithm for max flow, which is secretly the same as min cut, those two running times are actually comparable. Right? So here what we have is a very simple randomized algorithm with a fairly simple analysis where the running time is comparable to the running time of the best deterministic algorithm. So, one advantage of something like this is this algorithm is so simple, it's actually much easier to code than the traditional deterministic algorithm, and you're much less likely to make an error when programming this. Right? So there are always trade-offs between using deterministic and randomized algorithms, even when the randomized algorithm has better behavior. But in this case, particularly if you were doing this by hand, I would highly recommend this algorithm to you. Right? And that's one of the advantages that we see over and over again with randomized algorithms.